Hello everyone, so welcome to lecture number 19, and in the previous lecture we have seen that how Langmuir's adsorption isotherm equation was derived. So in this lecture we are going to start with how far we can apply the Langmuir's adsorption isotherm equation and what are its limitations. So let me first refresh your memory. So Langmuir's adsorption isotherm actually relates theta, that means the number of molecules actually occupying the surface over the total number of molecules needed to form a complete monolayer. So this is a fraction. So in other words, this is called the fraction of gas molecules adsorbed, theta, how it is related with the pressure of the gas molecules. All right, so theta is equal to bp divided by 1 plus bp, where b is a constant, which is nothing but the equilibrium constant of the entire adsorption desorption process multiplied by e to the power ea by RT, where ea is the activation energy of the desorption process and T is the absolute temperature. So the first thing we come at is to discuss the practical utility of the Langmuir's adsorption isotherm equation. So the most useful application of this equation is the estimation of the surface area of the adsorbent. Okay, so that means whatever the solid surface that we are using to adsorb gas, using Langmuir's equation we can estimate the surface area of that solid. So how it is done? So if we look at this equation here, theta, so if we take theta means n divided by nm is equal to bp divided by 1 plus bp. So if we take the reverse of it, that is nm divided by n is equal to 1 plus 1 over bp, isn't it? So now what I'm going to do is I will multiply nm in the denominator in both sides. So therefore we have an equation like this: 1 over n is equal to 1 over nm plus 1 over nm multiplied by b multiplied by 1 over p. Now you can simply see that this equation is in congruence with a straight line equation, right? So y is equal to mx plus c. So therefore if we are going to measure the pressure versus the number of gas molecules adsorbed, and then if we try to plot them, plot what? So we need to plot that how with respect to the change of pressure 1 over p is plotted with the inverse of the number of gas molecules adsorbed. So this graph would give me a straight line. Okay, so the points would come like that, and if we make a best fit straight line, then therefore the slope would give me the value 1 over nm multiplied by b, and then the intercept itself would give you 1 over nm. All right, so this is the slope and this is the intercept. So therefore if we take the reverse of the intercept, so whatever the value of the intercept, if we take the inverse of the intercept, it would give me nm. That means this is the number of gas molecules required to have a complete monolayer adsorption. So if we can recollect the Langmuir's adsorption model, so that means that only complete monolayer is formed once all the gas molecules are occupying all the possible places. So what the number of gas molecules needed to cover the surface would actually give the estimation of the surface area. So that means if I know nm, then if I simply multiply it with the molecular cross section sigma, which is often calculated in nanometer square or angstrom square, and then we can easily measure directly the surface area of the solid surface. So now oftentimes what happens, if you talk about the practical aspect of the adsorption, the instrument itself, instead of recording the number of gas molecules adsorbed, it directly measures the volume of the gas molecules adsorbed. All right, so what it does is actually the volume adsorbed. So the same equation over here can be replaced, V divided by Vm, where V is the volume of gas molecules adsorbed at any time point, over Vm, the volume required to have a complete monolayer, can be replaced exactly like this. So therefore the equation then takes place into something like this. Instead of 1 over nm, instead of 1 over n, it has the 1 over v term. All right, so the rest of the things is the identical. So the graph plot also becomes identical, but instead we have 1 over v. So the reverse of intercept would definitely give you the v, that is the volume adsorbed. Okay, Vm, definitely volume adsorbed when a monolayer is complete. Now this volume recorded obviously at a very low temperature. All right, because I have already told you the adsorption process takes place at a very low temperature. So what happens, the machine itself transform this value into the Vm at STP, that means at standard temperature and pressure. And we know once we get the volume at standard temperature and pressure, and we know that how much 1 mole of a gas occupies the volume at standard temperature and pressure. So from that we can easily calculate from Vm the Nm, that means first the number of moles, and from that the number of molecules required to complete the monolayer, Nm, and from once we get the Nm, we can have the molecular cross section from the literature data, that is sigma, and we can easily calculate the total surface area of the solid adsorbent. So this is the practical utility of the Langmuir's equation for the adsorption isotherm. So now we will discuss that how far the Langmuir's theory is can be applied, and it is true in what extent. So therefore I'm going to erase the board and we will start discussing the limitations of the Langmuir's theory in explaining the adsorption process. Okay, so let's do it. So according to Langmuir, if someone wants to plot 1 over volume adsorbed versus 1 over pressure data, we will have some data points, and those data points should be fitted ideally with a straight line. So like we have these kind of few scattered points, and we would like to draw a best fit straight line out of those data points. But after Langmuir's introduction of his adsorption theory, research on different types of adsorbents with different types of adsorbate took place extensively. So people started out to generate a whole lot of different types of data. So one thing was immediately observed, that according to Langmuir, whatever data points that were supposed to be linear, if we try to plot 1 over v or versus 1 over p, so this 1 over v versus 1 over p data has not been found to be linear over all ranges of pressure P. So that means in many systems what was observed, that the linearity of 1 over v versus 1 over p is limited within a very short or certain range of the pressure. So this is number one, the first observation that deviates from Langmuir's expectation. Number one. And number two, as I told you, that with the advent of the research on adsorption, various different types of adsorption isotherms were discovered, which are a lot different from whatever the adsorption isotherm explained by Langmuir theoretically. So let's start with that. So the type that Langmuir explained, it was kind of like that. Okay, so it's first kind of you see an exponential rise, and then it flattens out. Okay, so anyway, so we can plot this V versus P plot. So these are adsorption isotherm. Now, according to International Union of Pure and Applied Chemistry, IUPAC, they recognize different patterns of adsorption isotherms, and they categorically told these that these are of certain types, like type 1, type 2, type 3, type 4, etc. So the type of the adsorption isotherm explained by Langmuir, which resembled some graph plots like this, according to IUPAC, this is called the type 1 adsorption isotherm. Okay, so I can write it here, type 1 adsorption isotherm. All right, so now you'd be surprised to know that there are so far 5 or 6 different types of adsorption isotherm recognized by IUPAC. So here in this course we would contain our discussion only up to 4 types. So this is type 1, and then again, so V versus P. All right, so we have this kind of adsorption isotherm adsorb. All right, now you see the first part over here, it's almost look like type 1, but after that it completely deviates from type 1. So this type of isotherm is called type 2. And then here we have type 3. So this is P over V. All right, so this P can be replaced by P over P naught, so that's a very trivial thing. So for type 3, you see the adsorption isotherm takes resembles something like this. So this is type 3, and you see at the low pressure region this curve is completely different than these two, but at high pressure region this resembles with type 2. Okay, and then there is type 4. So this is P versus V. So type 4 would be a kind of a mixture of type 1, type 2, etc. So the type 4 would become something like this. So it would rise like this, and then again flattens out, and again it can have another rise, and again that's gets flattened. Okay, so wherever we have this scenario, we call it type 4. So the most striking feature of type 4 is that we have two rising region, right? One is the first rise, and this here we have the second rise. So the two kind of rise is not present here, either in type 1 or type 2 or type 3, because here also we have a rise, but it is completely different than this type 4. So these are very typical, and you are supposed to memorize these 4 types so that you can easily recognize whenever you come across these. Remember, there are other types also, but for the time being I'm not going into that. We are confining our discussions only up to type 4. Now let us come back. So coming back, then obviously you see Langmuir's adsorption isotherm is good enough to explain only this type of adsorption isotherm. With that means with the equation theta is equal to BP over 1 plus BP is not good enough to explain type 2, type 3 and type 4. And more importantly, the type 2, type 3, type 4 are demonstrated by different kinds of adsorbents with a variety of gas molecules. For an example, the type 3 adsorption isotherm is shown by bromine 2 gas on silica gel. All right, so and also like H2O vapor on charcoal. Okay, means moisture on charcoal typically shows the type 3 isotherm, so which is completely different from the type 1, and there is no answer from Langmuir's theory how to explain those. So the next question is, was there any theory that came up to address all those four kinds of different adsorption isotherm? So let me tell you, there were quite a few theories that came up to explain all of these, but so far there is not a single theory that can explain all these uh, observations with 100% accuracy. But still, there is one theory that came up 20 years later after Langmuir, which was successful enough to explain the majority of this observation. So that means that theory may not be 100% accurate, but it's accurate enough so that till date it is accepted as one of the most abundant, common or popular theory to explain all these kinds of adsorption behavior. So our job is to study that advanced theory a little bit. Okay, so let me erase the board and we will start a fresh look at a new fresh theory. All right, so let's do that. So the theory that I was talking about is widely accepted now, is known as BET theory. You must have heard about it perhaps, but it is based on the work of three scientists whose last names were Brunner, Emmett and Taylor. So it summed up with the first letter of their last names, B, E and T, that makes the abbreviation BET. All right, so it was introduced in 1938. Now the theory exactly started from the assumptions where the Langmuir's treatment was somewhat incomplete. So in order to understand that, let's first with what Langmuir assumed. So Langmuir's assumption was mostly on that the adsorption is limited to monolayer only. Okay, so that means on the solid surface where there are the designated adsorption site, so only one molecule sits on the adsorption sites and there is no provision of formation of multilayer. All right, so this is not wrong, of course, because this is possible, and we have seen just few minutes ago that the type 1 adsorption isotherm that quite satisfactorily conforms to the Langmuir's theory V versus P, and this is type 1. So this type 1 in type 1 adsorption isotherm, the adsorption in fact is limited to the monolayer only. So microporous materials mainly exhibit type 1 adsorption isotherm. So what are microporous materials and why it shows type 1, we'll come to that later, but the fact is the assumption is not wrong, but if we strictly adhere to this kind of assumption, we would be only able to explain the type 1 adsorption isotherm. All right, so now what BET's assumption was that they said that both monolayer and multilayer adsorption take place simultaneously, and not only that, the how many number of multilayers are possible, the answer is they assume that infinite number of multilayers assumption. possible. So therefore, in BET model, on the adsorption sites, there could be only one molecule sitting, there could be no molecule sitting, there could be two molecules sitting, and so when there are two molecules, we call it the multi-layer, because one molecule is sitting on top of the other. So here we can have three molecules, and here we can have four molecules, and here we can have some more number of molecules like that. So therefore here we have monolayer, means one molecule sitting on the adsorption side. L is equal to 1, here L is equal to 2, 3, 4, and here it is multi, so we can call it is I. So there are ith layer possible. Now this L, okay, so here L is 0, okay, because here is no molecule sitting on that place. So the L, that means the number of layer, can start with 0, can be 1, can be 2, can be 3, can be I, can anything, and this goes up to infinity. So there could be infinite number of multi-layers possible. But one thing we must remember, that all those things according to BET are happening at the same time. So that means once the adsorption process is going on, it is very well possible that on these adsorption sites, there are some sites that is completely vacant, some sites with only one molecule, some sites with I number of molecules, means ith layer, and also there is possible an infinite layer is there. Okay, so that was the major difference of the BET's assumption with the Langmuir's assumption. But that's not all. That was the first difference. Okay, so in terms of multiple layers, or means the multiple layers of BET versus monolayer of Langmuir's adsorption isotherm. But let me tell you the why BET theory is more acceptable than Langmuir, because we will try to see that whether whatever the equation that comes out from BET's treatment, whether that equation should be good enough to explain type 1, type 2, type 3, and in some cases type 4. So that we will figure it out later. But for the time being, let's quickly address the other major difference that was lying there. So obviously, when Langmuir assumed a monolayer of adsorption, so that means the activation energy EA, that of desorption, is only of one type, that is the interaction between the solid molecule versus the solid, the interaction between the gas molecule versus the solid surface. So here this activation energy is mainly between the molecule and the solid. All right. But once there are multiple layers, so we encounter two different interface. So one interface is exactly this, like Langmuir's one, that means the gas molecules versus the solid. But here what's happening in multiple layers, we have a different kind of interaction, that is the interaction between two molecule interaction, and here we have the molecule solid interaction. So therefore in BET we come across two types of activation energy. One is E1, so E1 is the same as with the Langmuir's one, that is the interaction between the gas and the solid, and EAL. So here L stands for liquid. Why? Because once the gas molecules get adsorbed on the solid surface, so the interaction energy between two corresponding gas molecules are almost equal to the liquid-liquid interaction. Okay, so it behaves, so these two gas molecules once adsorbed behaves like condensed phase, like behaves like a liquid phase. So that's why we consider that the activation energy of desorption as EAL. So therefore in BET theory we have two different kinds of activation energy. One is EA1 and another is EAL, So that EAL part obviously was missing when we considered Langmuir's monolayer adsorption. So now we are at a position to understand the Brunner-Emmett-Taylor or the BET theory. All right. So right here in this course, in the next lecture, I'm going to derive the BET theory or the BET equation. Although it's a bit a lengthy derivation, but it's worth it to derive because of the two reasons. Number one, the derivations of BET theory is not available in the physical chemistry textbooks that we come across normally. And second, once we understand the derivation, we will be at a position to able to understand that how the BET theory helps to explain all the different types of adsorption isotherm. So that derivation part we'll do in our next lecture, that is lecture 20. So let's look forward to that, and till then, stay safe, take care. So goodbye, and I'll see you in the next lecture.